Okay, in this problem we need to sketch the graph of this polynomial function. Of course, knowledge of the derivatives of y, in particular the first and second derivatives, will greatly aid me in this process. So let's find those first. What is y prime and y double prime here? Well, let's write y down first. Then, of course, y prime can be found quickly by applying the power rule to each one of these terms. So we have the first derivative. Of course, we can do the exact same thing to find the second derivative. Apply the power rule to each one of these three terms. And that will give this. Now, the way these things will help me, the derivatives and even the original function, with regard to graphing, is that each one of these things will reveal something interesting about the graph when these expressions are 0 and or undefined. But either way, to make these places more obvious, I want to express each one of these things in factored form. So, looking at the top one, it appears clear we can pull out a common x squared from all three terms, so let's go ahead and do that. Now it appears that we still have this remaining quadratic to deal with, but if we try to factor this into the product of two binomials just by reversing the FOIL process, we're going to be disappointed. However, I can still find out where this factor, this quadratic factor, contributes some zeros for the overall function by using the quadratic formula. Of course, when we do some of the arithmetic here, it looks like we're going to end up with a negative under the radical. Of course, that means that this quadratic has no real solution. Now, what about y prime, the first derivative? Can I express it in a factored form? Again, the idea here is to make it easy to identify when the first derivative and later the second derivative is equal to 0 and or undefined. Well, if we're trying to factor this again, we can pull out a common x and a 4 from each term here. So let's go ahead and do that. Here again we're left with a quadratic. However, this one very quickly factors as the square of a binomial. Okay, so now we have this in a completely factored form. So now let's turn our attention to the second derivative. Here again I want to get this in a factored form, and I can start by looking for a common monomial. Here it looks like we can pull out a 12 out of each of these three terms. So let's do that. And once again we're left with a quadratic, and here, just like the first derivative, this one factors rather quickly. 12 times the quantity x minus 3 times the quantity x minus 1. Here again, second derivative is now fully factored. Now, in looking at these three factored expressions, it's fairly easy to identify what x values will make each of them 0 or undefined. Again, they can't be undefined because they're all polynomials, but they can be 0. This top one, of course, will be 0 when the first factor is 0. So that's when x itself is 0. And recall, this second factor is never 0. It has no real solutions here when we set it equal to 0. So I'm going to indicate that we have some interesting behavior at x equals 0 by drawing a little number line over here to the right and marking 0 on that number line. Then I'm going to do the same thing for the first derivative. I'm going to ask myself the question, where is it 0 and or undefined? Of course, it's not undefined because it's a polynomial, but it is 0 when this factor is 0, and consequently when x itself is 0. It is 0 when this factor is 0, and consequently when x is 3. So it looks like we have some interesting behavior at 0 and 3. And so I'm going to draw a second number line down here for the first derivative, marking those two locations. Just like this. Now that done, let's turn our attention to the second derivative and ask ourselves the same question, when is this expression 0 or undefined? Again, it's never undefined because it's a polynomial function we started with, but it is certainly 0 when x is 3 and when x is 1. So again, let's create a number line down here with those points marked. Okay, so what does this tell me graphically about this function? Why is it important that I know when the original function is equal to 0? Well, y equals 0 means the graph here is 0 high. So at x equals 0, we are 0 high, we have an x-intercept. So let's label that accordingly. As for y prime, the first derivative, when this is 0, the slope of our tangent line must be 0, which means our tangent line is horizontal. So at 0 and 3, we have a horizontal tangent. So let's label those. And then with regard to the second derivative being 0 means we might have a point of inflection. We don't know that for sure because I don't know what the concavity is on the left and the right of these 2 points. Only if the concavity changes, of course, from concave up to concave down or from concave down to concave up, do I have a point of inflection. So let's not label that just yet. Rather, let's turn our attention to the actual concavity in each of the intervals produced. Of course, we know whether a function is concave up or concave down by looking at the sign of the second derivative. If this is positive, then it's concave up. If this is negative, then it's concave down at any given point. Once again, having the second derivative, and later on we'll see the first derivative and the original function in a factored form, makes finding out where this is positive or negative fairly easy. Look, consider any point here to the right of 3. Mustn't this factor here, x minus 3, be positive then? Consider a test value, say x equals 5. 5 minus 3 is 2, that's positive. Mustn't this factor of x minus 1 also be positive? Sure. Again, 5 minus 1 is 4. That's positive using a test value. So a positive times a positive times a positive 12 is positive, which means everywhere to the right of 3, the second derivative is positive, which means everywhere to the right of 3, the graph should be concave up. So let's indicate that with a little cupped U here. Likewise, if we're to the left of 3, but to the right of 1, this is now negative, this x minus 3, while this is still positive, the x minus 1. So now we have a positive times a negative times a positive. That product must be negative, which means in between 1 and 3, this function has to be concave down. So let's indicate that. And then to the left of 1, notice both of these factors, x minus 3 and x minus 1, must be negative. So now we have a positive times a negative times a negative. That's positive overall, which means in this interval we are once again concave up. Okay, so we indicate that. Now it's pretty clear that 1 and 3 were indeed points of inflection. Look, we're going from concave up to concave down, and we're going from concave down to concave up. So let's label those 2 things. Now, just like we analyzed the concavity of the function by looking at the sign of the second derivative, we can also look at the sign of the first derivative and find something interesting about the graph. Recall, if the derivative is positive, our function must be increasing, and if the derivative is negative, our function must be decreasing. So noticing that we have 3 intervals here as well, we do a sign analysis on each interval back in the first derivative's factored form and see what we get. If we're to the right of 3, of course, this factor must be positive, this factor of 4x must be positive, and so product of those 2 positives gives us a positive first derivative, and hence in this interval our function must be increasing. So I'll indicate that with a little rising line here. Between 0 and 3, notice 4x is positive, however x minus 3 is now negative, but we're squaring it, which forces it to be positive once again. So here again the product is going to be positive, and here again in between these 2 points our function is increasing. Now to the left of 0, our 4x is now negative, and x minus 3 is also negative, but it's being squared. So this whole thing here is positive times this negative makes y prime negative, and hence to the left of 0 our function is decreasing as we move from left to right. If we wanted to, we could even go back to the original function and do this same sort of sign analysis, finding out where this expression is positive and where it's negative. We only have 2 intervals to check. One quick note, recall this quadratic factor had no real solutions, so just the graph of this little guy right here, just the graph of x squared minus 8x plus 18, consequently has no x-intercepts of its own, which means it sits entirely above or entirely below the x-axis. We can figure out which one by plugging in any point. Keeping in mind what we saw over here, I'm going to pick the point 4 because that's going to be where the vertex is going to be. Plugging 4 into, again, just this quadratic factor, we see we get a positive 2 out. And so the graph of, again, just this factor must lay entirely above, because that's positive, above the x-axis. Something like this, perhaps. Now, why do I bring that up? Well, to make the note that this factor, since it is always above the x-axis, is always positive, and thus always contributes a positive in terms of the sign analysis we must do. So going back to our intervals here, if I pick anything to the right of 0, notice this factor must always be positive by our argument we just discussed. This factor must also always be positive for a couple of reasons. X itself is positive, and notice it's been squared. So y itself is positive here, which graphically means our graph sits above the x-axis. So we'll indicate that here. And then on the left side of 0, notice again, this must always be positive because of the square, even though x itself is negative. And this is always positive because of this analysis. So again, the product is positive, and again, we are above the x-axis. So we mark that as well. Now, being a polynomial, there's just one more thing we need to turn our attention to before we start graphing, and that is the special points on our graph. Notice we have an x-intercept at 0, we have a point of inflection at 1, we have a point of inflection at 3, and a horizontal tangent there as well. These are all x-coordinates. We need to know the y-coordinates that go with them. So let's make ourselves a little t-chart with those particular x values marked. Then as for the y values, notice at least for x equals 0, since we had an x-intercept there, the function must be 0 high, so y must be 0. At x equals 1, we can find out what the y-coordinate should be by appealing to the original function, simply plugging 1 in. Of course, doing that we have, so we put that here, and then as for x equals 3, we can find y in the same way. We can either plug it into here, or if it's more convenient, perhaps plug it in to this expression. Doing so, we get 9 times all this mess, or equivalently, 27. Now we have, right here, all of the information we need to graph this function. Let's note we have 3 points that we should plot, a point at 0, 0, a point at 1, 11, and a point at 3, 27. Let's mark those on our graph. Noting that I have horizontal tangents at both 0 and 3, we'll do this. And at 0, we'll do something similar, although it's a bit hard to see here. From here, I want to take it one interval at a time. Look, I've got my real number line broken into really 4 intervals. We have the interval from negative infinity up to 0. Then we have what's going on between 0 and 1. Right? The behavior changes at 1. And then we have the behavior of the function between 1 and 3. Again, the behavior changes at 3. And then we have the behavior of the function from 3 on. Let's take that first interval. Notice we have to be above the x-axis, decreasing in a concave up way, and we have to end up at 0 with a horizontal tangent. There's really only one way you can draw that. Okay, there we go. Now, between 0 and 1, we have to be above the x-axis, we have to be increasing, and we still have to be concave up. Again, really just one reasonable way to draw that, like so. As for our next region, from 1 to 3, we are still above the x-axis, we are still increasing, but now we're doing so in a concave down way. We must end here with a horizontal tangent. So let's draw that. Lastly, from 3 to infinity, we stay above the x-axis, we start to increase, or continue to increase, I should say, and we return to being concave up. So again, just one way to draw that. And there we go. We might want to mark some of these interesting points, noting in particular at the origin we have a local minimum. Y prime tells us this, the function's going down and then it's going up, but the graph tells us it's not just a local min, it's an absolute min. That's the graph. Hope that helped.